So welcome back everyone. So in this lecture we will continue our discussion on the symmetry elements. So till now what we have talked about, the individual symmetry elements. We have talked about rotations, mirror planes, inversion points. We will move to the next level and look at the combinations of these symmetry elements. For example, let us say that you want to combine a 6-fold with a 2-fold rotation. You want to combine a mirror plane with a 4-fold and all. So we will discuss how can you combine these symmetry elements. It is not that you can combine any of the symmetry elements with another one in any fashion. There are some set of rules that you would have to follow, and we will discuss those rules. So before we begin with that, let us look at this example. So I've created this figure. What is this? This is a hexagonal prism. Why is it called hexagonal? Because if you look from the top, what you will see? You will see a single hexagon. And why is it prism? Because it is extended in one of the directions. For example, if you look at this bottle, the top view is a circle and it is extended in this direction. So the top view for our image is a hexagon, and you have extended it in such a manner, but with what I'm calling as the C direction. So this is a hexagonal prism. What different symmetry elements can you see in this image? I can see that there is a 6-fold rotation going inside the center through the prism. So there is a 6-fold rotation going on, right? Okay. There is also a mirror plane going through the center of the prism. So if this is your prism, you have the 6-fold going through it, and you have a mirror plane inside the hexagon as well, a mirror plane cross-cutting the hexagonal prism at the center. Why? Because not this bottle is different at the top and at the bottom, but if you look at our hexagon, the part of the hexagon above the mirror plane is an exact replica of the hexagonal prism below the mirror plane. That is why there is a mirror plane as well. You can imagine a lot many symmetry elements in this hexagonal prism. Now what is this telling us? This is telling us that at least there was a 6-fold and a mirror plane in this image. That means at least you can combine these two symmetry operations. And how have you combined them? You kept the 6-fold in the vertical direction, and the mirror plane was in the horizontal direction. That means the 6-fold was perpendicular to the mirror plane, right? So this is one of the fashions in which you can combine a rotation and a mirror plane. Now we will study what are the different rules that govern how you can combine these symmetry elements. So let us begin. So before we do that, there are two terms on this board. One of the term is finite and the other term is infinite. What do these signify? These signify that what am I looking at? For example, this bottle that we were looking at, this is a representation of the finite world. Finite world. That means this object has some boundaries. I can put it in my hand and I can hold it in my hand. Okay. If you look at these hand specimens, you can actually grab them in your hands. You can actually see where they are ending in 3D space. Where this pseudomorph of staurolite is ending, you can see with your eyes. Okay. So these are examples of the finite world. For example, this mineral. This mineral has a hexagonal appearance and it is a prism extended in this direction. So the hexagonal prism that we have talked about earlier. Any guesses what this mineral may be? This mineral is actually a mineral called beryl. So you make this connection in your mind that beryl is associated with what shape? It is associated with hexagons. Okay, so for example, in the examinations that you're preparing for, you have 2 columns. one has beryl and the other one has hexagon. So beryl must be associated with the hexagonal column. These are some small trivia that we will go on, we will intake as we continue with our main lectures. So for now, what we want to remember beryl is associated with hexagons. Okay, we don't want to remember the composition of beryl, just that beryl, when beryl comes to our minds, hexagons also come to our minds. Okay, so back to finite and infinite. So this is a finite sample of beryl. Why it is finite? Because I can hold it. Now what happens when I zoom into beryl? If I take this specimen and I zoom into the hand specimen, let us say to the order of 10 is per 20, 10 is per 40, 10 is per 10, such high magnitudes of magnification. What happens when you zoom into these levels of magnification? You actually land up at the atomic scale. So this is the atomic scale photograph of a hand specimen of beryl. And what you can see hexagons. You can see a hexagon here. You can see a hexagon here, a hexagon here, multiple hexagons. We have already discussed this. What is this property? This property is called translation. That you are copying, pasting a hexagon in multiple directions, and this is what we know to be as translation. Okay, so this is a sixfold. A sixfold also exists at this place. There is another sixfold here, another sixfold, another sixfold, another sixfold, another sixfold. There are multiple sixfolds in the infinite world. What about the finite world? Where is the sixfold? You just have one sixfold here. One single sixfold going through the center of the object that is our beryl hand specimen. So one difference that I can make out is that in the finite world, I had just one sixfold rotation. While in the infinite sequence, I can make out that there are multiple sixfold rotations possible. So the difference between these two images is that there is no combination of sixfold with any sixfold. You have infinite number of sixfold rotation axes. So because of this, because the infinite image has n number of sixfolds, or because we are talking about sixfold, if we talked about another mineral, n number of rotational symmetries, n number of mirror planes. That is why the rules that apply to finite world and the rules that apply to infinite world are very different. You cannot say that the rules that are followed in the finite world would be followed here, and vice versa. So we have to discuss these two scenarios in different classes. Right now, what we will discuss? We will discuss the finite scenario. Why? Because earlier also we have talked about symmetry elements of rotation, mirrors, inversion, and roto-inversions. These symmetry elements can exist without translation as well. So our focus earlier and today is in the finite world. We are not talking about the infinite world. We are not talking about systems in which translation can occur. Okay. So keep this in mind. Whatever we talk about is in the finite world, is in the hand specimen scale. Okay. What your books call as external symmetry. External symmetry. Okay. Symmetry that you can see outside the hand specimen, not at the atomic scale. Now let us look at how can you combine it. What are the rules that you have to follow while combining symmetry elements? Take a look at this image. I hope you are familiar with this concept. What this image is showing us is that if you have a mirror plane here, let us say, and you have a mirror plane exactly parallel to that mirror plane. For example, in this washroom, what you had was you had a mirror plane in the front wall as well as a mirror plane at the back wall. So what happens is that when you place two mirror planes parallel to each other, this mirror 2 creates a mirror image of the first mirror. Now this mirror 1 will look at these two mirrors and generate a mirror image of the M2 mirror and a mirror image of the first mirror that was generated by M2. And this sequence will go on till infinity. Okay, that is why when you have this placement of two mirrors, what you see is that the reflection goes on till infinity. Why? Because these two mirrors are completely parallel to each other. If you have not seen such a thing, what you can do is that in your homes you must have a wall with a mirror. You buy a small piece of mirror and place it exactly parallel to the wall mirror. What you will see such a pattern going till infinity. Now this is mirrors that we are talking about. Let us talk about rotations now. Let us say we have a twofold rotation here and you have another twofold parallel to it. So you had one twofold and you had another twofold. So what will happen? If this is the twofold that I want to look at first, what this will do, it will create a copy of the other twofold axis. So this twofold generates a copy of the red twofold generates a copy of the yellow twofold axis. Now you have three twofold axes in your system. Now what will happen? You take any of the twofolds. If you take this twofold, what will this do? It will look at this red twofold, generate a 180-degree copy. It will also look at this twofold and generate another copy. And this sequence will also go on till infinity. You will have infinite number of twofold axes. And why did you have that? It was because the initial twofold axes that you placed, they were parallel to each other, just like mirrors. Okay, so whenever you are combining symmetry elements that are parallel to each other, you get sequences that go till infinity. Now it is possible, it is very possible that you can take sequences till infinity, but you can take sequences till infinity in the infinite world only, not in the finite world. In the finite world, the specimen has to end. Okay, obviously this infinite world has some boundary, it is ending at some point, but the scale at which you are looking at this scale, it looks like it is going till infinity. But the hand specimen, because it has a fixed volume, you cannot have such arrangement in a hand specimen. So the possible combinations in which you kept the symmetry elements parallel is not possible. You cannot keep symmetry elements parallel. You cannot have a rotation parallel to another rotation. You cannot have a mirror plane parallel to another mirror plane. Is it possible that I place them at a random angle? No, this is also not possible. If you are experimenting with those mirrors, for example, you had a mirror on your wall, you bought a small mirror. If you place that small mirror at a random angle like this, then also the sequence goes till infinity. Okay, so you cannot keep symmetry elements at a random angle as well. Okay, not parallel, not at a random angle. What are the conditions that are left? One of the conditions that is left is that you keep them perpendicular to each other. For example, you had this twofold axis and you kept another twofold axis like this, perpendicular to it. So if you look at the red twofold axis, what will it do? It will rotate anything in such a manner, in a vertical circle. So this twofold, it can rotate this yellow twofold axis in the orientation in which the yellow twofold axis uh, existed prior to the rotation. What I meant was that if this is your twofold axis and this is the red twofold axis and this is the yellow twofold axis, if the red twofold axis rotates, it rotates the the yellow one in such a manner. So the yellow one was initially like this, now it is exactly like this. There is no change. So when you combine symmetry elements perpendicular to each other, you do not create a sequence that goes till infinity. This was the initial combination and this is the final combination. Okay, if you moved using the yellow twofold axis, you got this figure. You started with this and you got this. Okay, exactly same. There is nothing that goes till infinity. So this is permissible. This is allowed for external symmetry. For external symmetry, you can combine rotations perpendicular to each other. You can combine mirror planes perpendicular to each other. That is perfectly fine. You cannot combine them in parallel, but you can combine them at 90 degrees or perpendicular to each other. Now, there are some special scenarios. Some special scenarios which we will later look on, which are called isometric scenarios or isometric systems. In these systems, there is a possibility, there is a special possibility that you can combine elements at this angle. The value of that angle is 54 degrees and 44 minutes. So if you have a rotation like this, you can have another rotation and the angle should be 54, 44. This is very limited scenario. This is applicable for very limited scenarios, and those scenarios exist in isometric systems only. Okay, nothing, nowhere else. Commonly, you can just combine symmetry elements perpendicular to each other in isometric systems. In some special cases, you can combine them at this special angle as well. Now let us, I don't have a cube. Okay, if you have a cube, that would be better for this demonstration. Let us imagine that this is a cube. Okay, you see a rectangle at the front. If it would have been a cube, you would see a perfect square. Let me draw that square. Sorry, that cube. A and B. So if you combine this line segment AB, this is called as the body diagonal. Okay, a diagonal is something that creates, that joins the opposite ends of a face. A body diagonal joins the upper vertex of the cube with the exactly opposite vertex at the bottom of the cube. Okay, you can also say that A and B are inverted images of each other. For example, A is behind at the top and to the right. So the inverted image of A would be in the front, at the bottom, and to the left. So A and B are related by an inversion center, and these lines are known as body diagonals. For example, C and D, E and F. All these lines are body diagonals. Okay. So now if you can imagine that cube, if you can imagine a body diagonal, okay, what I want you to question yourself is that when you talk about cubes, what is the rotational symmetry that you talk about? You talk about fourfold rotations. Why? Because every face of the cube is a square. That means you have a fourfold going here, a fourfold going here, and a fourfold going here as well. Through every face, you can imagine a fourfold going. Okay. What if I ask you, can you imagine a threefold rotation in a cube? Is it possible that a cube has a threefold rotation? Yes, it is quite possible. Where is that threefold? Along these body diagonals. For example, you take your book and you look through it. Okay, you look through the body diagonal. For example, if you're looking through this part of the book, through the body diagonal, what you see? You see one line is going through towards me, one line is going at the bottom, and one line is going in the east-west direction. Now the line segments, the length of these line segments is different because we are not talking about a perfect cube. If this would have been a perfect cube, the line segments would be exactly the same length. So if you look through the body diagonal, what you see? You see something like this. I have this cube. You see this pattern. What you see is that the three lines are originating from this vertex, and the angle between them is 120 degrees. That means you have a threefold rotation inside a cube as well along the body diagonal. Okay, you take, if you don't have a cube, you take your books and you try to see that yes, there is a threefold going on. So now this threefold, this body diagonal in cubes is at an angle of 54, 44 minutes. That is why we said that this is a special angle that only exists in isometric system, which for our cases is represented by a cube. Okay, I will show you an animation here. For example, if you take this cube, you were able to see those three lines originating. Okay. You can see that there are three lines originating, and you have that four-fold symmetry in this phase, while you have a three-fold symmetry through the body diagonal. So you can rotate this and you can try to figure out where is the threefold. There is another threefold here through this body diagonal. There is another threefold through this body diagonal. So a cube has a threefold through the body diagonal. Okay. So what you have to remember that rotations, when combined with rotations, are perpendicular. Mirrors combined with mirrors are perpendicular. And there is a special scenario of this random angle in isometric systems only. Now let us move on. Now this is an empty room. Okay. Why I have this image? This is the image of an empty room. Now crystallography, a lot of crystallography is imagination. You have to imagine a lot of things to be able to figure out what is going on. This empty room will help us in imagining. For example, you are sitting in whatever room you are sitting in. I hope it is cuboidal, not oval. So what you have to do, you look for a vertical pillar. You look for your vertical pillar like this. So this is a vertical pillar, right? Now if you follow this vertical pillar where it meets your floor, you will see there are two edges coming out of it, right? You saw your pillar, you look at the bottom, and you will see one of the walls has that edge and the other wall has the other edge going through it. If you want to imagine this in a Cartesian system, you have the z-axis, you have the x-axis, and you have the y-axis. Now, what is common between these pillars and the Cartesian space? The Cartesian space x, y, z, and x, y, and z are perpendicular to each other. Same is the scenario with your pillars and the edges as well. They are perpendicular to one another. Now, why is this important? Because earlier we talked about you can combine systems, symmetry elements perpendicular to each other. Now, if you can imagine this room, you can say that the vertical pillar is a four-fold rotation. This edge is a two-fold rotation. This other edge is also a two-fold rotation. So using this room, you are able to imagine at least three rotational symmetries. And because you can only keep them perpendicular to each other, so there is no distortion in the image as well. Whatever your room looks like, that is the location of these three rotation axes. If you don't want to imagine the room, you can imagine the Cartesian as well. The z-axis becomes the four-fold, x-axis becomes the two-fold, and the y-axis becomes the two-fold. So this room or the Cartesian helps us to imagine where do I place these three rotation symmetry axes, because I can only place them perpendicular to each other. Now, what about mirrors? What about mirror planes? How do I imagine mirror planes? Same, you go back to your room. You can see that there is a floor. You have this wall, and you have this wall as well, right? In the Cartesian, z, x, and y. What is the floor in the Cartesian? The floor in the Cartesian is the xy plane. What is wall 1? It is the zx plane. And what is wall 2? It is the zy plane, right? And what is the correlation between these three planes? These three planes are perpendicular to one another, right? These two walls and the floor are perpendicular to one another. If you are following the Cartesian, these three planes are perpendicular to one another. And how do you combine mirrors? You combine them in a perpendicular arrangement. So this room can also help you imagine at least three mirror planes that are perpendicular to one another. So using the analogy of this room, we are able to imagine 3 rotation axes as well as 3 mirror planes. Okay, so this is very beneficial. Now let us move on. Now I have these 2 rules. Okay, these are not official rules. These are some guidelines that I use to remember how do I combine things. Let us say, for example, you have something like this. You have something written like 422. 422 means you have a 4-fold rotation, you have a 2-fold rotation, and you have another 2-fold rotation at least. This is how you denote this combination of a 4-fold rotation, 2-fold rotation, and 2-fold rotation. You write 422. Okay. Now, what would be the angle between these 3? From our earlier discussions, we know that they have to be perpendicular. So the angle between these 3 are perpendicular. What if I write something like this? What would be the angle between these 3 mirror planes? The angle would be perpendicular to one another. So this is our first rule. First rule is the rule of likeness. Rule of likeness suggests that if you have written a combination of numbers, or if you have a combination of letters, that means you have a combination of same things. All of them are numbers, all of them are letters. So if you have likeness, the angle should be 90 degrees. Okay, this was clear from our earlier discussions as well. If you had same things, either numbers or letters, the angle between them is exactly 90 degrees. So if the rule of likeness says it is angle 90, what would be the rule of disparity? Rule of disparity would be if you combine a letter with a number. Let us say you are writing 2m. So you have a 2-fold rotation and you have a mirror plane. What is the angle between these two? The angle is 0 degrees or parallel. Okay. So the rule of likeness was 90 degrees. Rule of disparity is exactly opposite. Perpendicular, parallel. Okay. So when you write similar things, the angle becomes 90. When you write different things, the angle becomes 0 degree or parallel to one another. For example, let us, if you want to imagine 2m, if you want to imagine 2m here, what will I do? First of all, I take my rotational symmetry. I take my rotational symmetry of the maximum order. Here the maximum order is 2-fold, and I keep it as the vertical pillar. So this vertical pillar becomes my 2-fold rotation axis. Okay. Now the other element is 2m. Rule of disparity suggested to me that the angle between these two is supposed to be 0 degrees. That means they are parallel. Can you imagine the mirror plane here? If you imagine the mirror plane to be the floor, you are absolutely wrong. Why? Because the vertical pillar and the mirror plane are at an angle of 90 degrees. This is not what you want to draw. You want to draw a mirror plane that is parallel to this 2-fold or parallel to this vertical pillar. So this wall is parallel to this 2-fold, and this wall is also parallel to this 2-fold. So you had your vertical mirror. The 2 walls that are originating out of it are parallel to that vertical pillar. For example, if you look at your notebooks, if you had such a ruling, let us say your notebook pages are ruled and the rule lines are in this fashion. All these lines, they exist inside the page. And because they exist inside the page, they are parallel to the page. Okay. So because this vertical pillar existed inside both of these walls, that is why the pillar was parallel to these walls. What about the floor? If you take this sheet of paper and you put a hole through it using your pen, something like this. So now the pen or the line segment exists not inside the page, outside the page. and at an angle of exactly 90 degrees. So this is a scenario. This is the mirror that I'm talking about. This is the twofold that I'm talking about. This is a scenario of them being perpendicular to one another. This is a scenario of them being parallel to one another. Okay. So in your house, in your room, you have something like this. One mirror plane is here, another mirror plane is here. So because I just want to imagine one mirror plane, you can choose any of these walls and that would be perfectly fine. So I hope you would be able to remember rule of likeness says the angle is 90, whatever we discussed. Rule of disparity is exactly opposite to it. Okay, so when you combine different types of symmetry elements, you have to combine them at an angle of 0 degrees. Is it possible that you can combine different type of different type of symmetry elements at an angle of 90 degrees? Is there a rule 3 also? Yes, it is very much possible. For example, when you talk about likeness and disparity, you are only talking about a numerator. For example, this figure 4 by m. 4 by m means you are talking about a numerator and you have a denominator as well. So when you talk about these two rules, what you're talking about? You're talking about numerators only. You're talking about 422, MMM, MM2, 2M, 4N, 6M. Okay, all these things. When you're talking about only a numerator, you have to follow the rule of likeness or the rule of disparity. So the rule of disparity said 2M means the angle is parallel. What about 2 by m? Now 2 by m means the angle is 90 degrees. Okay, so this is the third rule that I have to remember. 2 means the angle is 90 degrees. MM means the angle is 90 degrees. 2M means different things, the angle is supposed to be 0. Different things, but one is in the numerator, one is in the denominator. The angle is supposed to be exactly 90 degrees. So this is the case 4 by m. So if you want to imagine this 4 by m, 4 by m means the angle between the fourfold and the mirror plane is 90 degrees. They are perpendicular to one another. In your room, if you want to imagine this scenario, how will you imagine? You will look to the vertical pillar, the z axis, and you will say that this is my fourfold. And the floor, the xy plane, becomes your mirror plane. Okay, so the vertical pillar becomes the fourfold, and the perpendicular plane to it, that is your floor, becomes the mirror plane. If you want to, you can imagine the ceiling as well instead of the floor. Both of them are perpendicular to this vertical plane. So this is how you imagine 4 by m. Now let us try to generate these figures. So what are those figures? Those figures are top views. If you look at our system, if you look at the system 4 by m from the top, how will you look? How does it look? So because the first element that we have to generate is a fourfold rotation. So first of all, I generate my reference grid. We have already talked about reference grids when we talked about rotations and roto-inversions. This is my first motif. Now the first motif is ahead of the line. So after a fourfold rotation, ahead of the line, ahead of the line, ahead of the line. For example, let us say you drew the reference grid and you started with this motif ahead of the line and you generated something like this. So now, if you want to check whether the diagram that you generated is correct or not, what you have to check for is that the first motif that you started from was ahead of the line. The second motif is ahead of the line. Third motif is ahead of the line. The fourth motif is not ahead of the line. So this diagram is completely wrong. You have generated something that is not true. So that is why either you start ahead of the line or behind the line and you check. You check for each motif And when you have checked, you can say, yes, I have created my fourfold perfectly. Now, where is the mirror plane? If the fourfold is going in the screen, the mirror plane is supposed to be the screen itself. Now, one thing that I would like to say is that, first of all, uh, today I am generating these, right? From next classes, we will generate a lot of these diagrams. So sorry, what I want is that you try to generate these diagrams on your own, and then you look at my videos and check whether what you have drawn and what I have drawn, they match or not. Okay, just looking at me won't help you. Second of all, when I generate these images, I am generating them on a screen. Okay, my fourfold is going into the screen. Okay, so what I do is that I imagine my fourfold to be a horizontal line. But we have already talked about that. If I talk about this fourfold, I take this fourfold as a vertical line, right? That means I am imagining this vertical pillar as this fourfold. But when I draw on the screen, I have to imagine it as a horizontal line. This is my limitation. But you people are drawing on a sheet of paper. Okay. So when I say fourfold is going in the screen, it is a horizontal line. For you, it is a vertical line because you are looking downwards and drawing these. So keep that in mind. If by mistake I say that I kept my fourfold horizontal, that is not true. I kept my fourfold as a vertical. I'm just drawing at a screen that is attached to the wall while you are drawing on a sheet of paper, and what you are drawing is supposed to be the better option. Okay, now let us do one thing. So we looked at this fourfold axis, we generated these four motifs, and where was the mirror plane? The mirror plane was cutting this fourfold axis. So what will it do? It will take these four motifs at the top and create an exact replica at the bottom. We have already talked about why I am generating these as open dots, because if you have the horizontal plane, any motif above the horizontal plane is a solid motif. Anything below the horizontal plane is represented by a open motif. Look at this image. This was the textbook image. Exactly the same. So we are done with this as well, right? हाँ, ठीक. Okay. Now, one thing that I would like to clarify. Okay, these two images were taken from two different books. If you look at this graphical representation, this graphical representation is of a square. That means you are saying a fourfold is present in these diagrams. That is true. We have drawn a fourfold. That is fine. What is the graphical representation of mirrors? Mirrors are represented by solid lines, right? So when you look at the image to the left, you see there is a solid line here and you see there is a solid line here. But we, in our system, we did not have any mirrors in these orientations. Okay. What we had was a single mirror in the horizontal orientation. We did not have these two mirrors. These two mirrors did not exist in our diagram. That is why they are missing in this image, right? Now these are notation schemes that different people follow. What we will follow, because the exam point, the exams that we are preparing for, what they are following is this orientation. Oh, sorry, this nomenclature. So the nomenclature that we will follow would be a mirror is represented by a line, a solid line. If you don't have a mirror, you do not generate a solid line. That is why you generated a fourfold and you generated this solid line representing the horizontal mirror, and you are done. You will never generate something like this. Okay, Because there was no mirror planes, you will never generate a mirror plane here. We will look into this graphical nuance later on as well. For right now, I just want to say, you do not mark these solid lines because they do not represent any mirror planes in reality. Now let us move on. Let us move on to this example 422. So you are combining 422. All of them are numbers. That means rule of likeness. That means the angle is supposed to be 90 degrees. Now you keep the maximum order of rotation as the vertical. So I kept the fourfold vertical and I kept the twofold horizontal. In your room, your pillar became the fourfold and the edges on your floor became the twofold axis. Okay, no issues. Now let us generate the top view. I drew my reference grid. This is my first motif ahead of the line, second motif, third motif, and fourth motif. So I have successfully generated my fourfold rotation. 1, 2, 3, 4. Okay. Now I have a twofold rotation as well. So let us imagine one of the twofolds. Let us imagine the east-west twofold first. So I'm imagining a twofold here. Okay, so this was my first fourfold, and now this is my first twofold axis that I want to imagine. I have these four motifs. What will this twofold do to this motif? It will take it, rotate it, and place it right here. What will it do with this motif? It will take it and place it right here. Okay, this motif goes to this, and this motif after rotation lands up here. Right? Now you can see that we started with a solid motif, and after rotation it became a open motif. Now why is that so? Okay, this is also very important. This is very important. Why? Because you would have to imagine these rotations perfectly. Open solid motif changing to an open motif and a solid motif not changing to an open motif are very different symmetry operations. You have to be very careful with this. Let us say that the motif that you were talking about was you yourself, and you are standing in this room. Okay, and this is the twofold axis that we are talking about. So what this twofold does, it takes me and rotates me in a vertical circle. So this is my position. Okay, I was in this room. What will the twofold do? The twofold will take me and place me right here. Right? I am here. This is my twofold. What it did, it took me, rotated me behind, took me to the adjacent room, but in the basement. Okay, not exactly behind me and in the basement, because the angle of rotation is 180. So what happened? I was standing above the horizontal plane. So initially I was a solid motif. Now I am standing below the horizontal plane. That is why all these motifs have turned into an open motif. So the first fourfold generated these four motifs at the top. Now this twofold, this twofold took all these four motifs and placed them at the bottom. If you want to remember an easier way to rotate, what you do, if this is your rotation axis, it has to rotate perpendicular to it, and you start with a solid motif, you end with an open motif. You start with an open motif, you end with a solid motif. Now let us imagine the third twofold. Now the third twofold, if the the first twofold, this twofold, if this in the west east direction, the other twofold must be in the north south direction. So this is my twofold axis, right? How will this rotate? This will rotate in this manner. So this took this solid motif, placed it here. We already had that motif. It took this open motif. We already had that already present. What this means is that when you generated the first two rotation symmetries, the third symmetry was automatically generated. Okay, and this will happen a lot in a lot of symmetry diagrams that we will draw. The third element would be automatically generated. Okay, so this is the scenario. This is 422. Let us look at a very clean image. So this is a clean image. Now again, you see these solid lines. These solid lines, a solid line represents a mirror. Okay, if you have a solid line and you have something like this, this represents a two-fold rotation. This represents a three-fold rotation. But a solid line itself represents a mirror plane. There was no mirror plane. So this diagram is incorrect. The placement of motifs is okay, but these solid lines should not have been there. For example, this one is perfect. You had the fourfold going inside it. You had your first twofold. You had your second twofold. Now you see that there are other twofolds as well. We will move on to that when we discuss 422 in detail. Right now, we have discussed 4 by M, 4 perpendicular mirror, 422, 422 perpendicular rotation axis. And we are done. We are done to how to combine rotational symmetry mirror planes together in an external symmetry scenario in hand specimen. Not in systems where you have translation and all. Not in internal symmetry. I hope this was helpful. Thank you.